Okay, this is section 2.3. Now we're working more general polynomials. Last time we worked with quadratics, so now we want to work with just polynomials in general. So let's see, polynomial functions, and their graphs. Okay, so first we begin by defining the polynomial form. And there's no easy way, I guess, to say it. They just write it out in all of its glory. So a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus maybe a sub 2 x squared plus a sub 1 x plus a sub 0. Okay, so that would be the form. The degree in this case is n. Basically just the highest exponent is the degree. And then the leading coefficient is a sub n. Okay, so, in the beginning they have some easy identification problems. You have g of x equaling 6x to the 7th plus pi x to the 5th plus 2/3 x. I think they have some where they just want you to identify in particular, is it even a polynomial? And this guy is, it has this particular form. So it's a polynomial. Then maybe they want to know the degree and the leading coefficient. So the degree is, in this case, 7, and the leading coefficient, you make sure you have the highest. So this is 7, 5, and 1. The highest degree is 7, so the degree is 7. And then the leading coefficient is 6. Okay. One concern in later classes is smoothness and continuity. So smoothness just means, are there any corners on it? And continuity means, can you draw it without picking up your pencil or pen? So we talk about that for a second. Smoothness versus continuity, or, continuity. So again, if it's smooth, that means it doesn't have any sharp corners. And then secondly, continuity. That means there's no holes in it. Okay, so no jumps, no vertical asymptotes, no holes. Okay. The more classes you take, the more rigorous they'll make these definitions, but in general, you have some example like this that would designate, you would be able to know this is not smooth. Okay, there's a big corner at the bottom of it. Whoops, sorry, I ran off the page there. Right here is a big corner there. So this is not smooth. It's continuous though. You can draw it without picking up your pen. Okay. On the other hand, this guy here is not continuous. So it has a vertical asymptote at x equals 0. Okay. Let's look at the end behavior of these polynomials. So section 3, end behavior. Okay, and there's basically just 4 different types, and it's based off the leading coefficient. Okay, so the book will call this the leading coefficient test. Okay. So if the degree is odd, you'll have one of these two cases. So it'll go and do something in the middle and then end up going out in that direction. So it's kind of like if you think of the equation of a line, it kind of looks like the equation of a line with positive slope. So you can think of that leading coefficient A as being the slope. And if the slope is positive, it kind of has this rising characteristic to it. And then, on the other hand, if the slope is negative, it'll fall like this. So it'll go down and then do some junk, and then it'll keep going down. So if it is a line, you can expect that this junk, there's no junk there. It just goes from here to here. Okay? But you can take that up a notch and talk about generalities. And if you have a higher degree polynomial with odd degree, like a cubic or a quintic or something like that, it'll have n behavior just like the formula of a line with this particular kind of slope, if you think of the leading coefficient as slope. Then we have n even, and these will behave just like polynomials. Okay, so you'll get a happy face in the end behavior for a leading coefficient that's positive. So for the parabola, it'll just go down like this. And then when the leading coefficient is negative, you get a sad face, okay, and doing something in between. Okay. So, in the book, in the beginning, they'll give you a polynomial, and you'll have to decide basically its form. And this would be the first step when we get to graphing. So it's just like with the quadratics, it's a happy face or sad face. It's the same kind of game here, except with a bit more stuff going on. So anyways, here the leading coefficient is 11. It's positive. It's greater than 0. Okay, and then the degree is 3, which is odd. Okay. So it'll have kind of our line with positive slope form. And I don't know exactly what it does, but it does some business in the middle. Okay. Let's look at 56. These are kind of like challenge problems. F of x equals -2 times x minus 4 squared times x squared minus 25. Okay, the deal with this is you're going to pick off the first term in each factor, okay, and multiply those together. And also we need to kind of connect this x to that squared. Okay, so the leading coefficient will be -2 times this part, the x squared, times this part here, another x squared. Okay, so the leading coefficient will end up being -2x to the 4th. So your leading coefficient a sub n is -4, which is of course less than 0. And then the degree is also, so the leading coefficient is -2, which is less than 0. The degree is 4, which is even. Okay, so you're going to have sort of the sad face behavior, whatever it does in the middle. But on the ends, it'll have kind of the parabola sad face. Okay. We'll be interested in seeing these places where the polynomials hit the x-axis. Basically, you're looking for, you're setting the thing equal to 0, and you're looking for the x-intercepts. And the book's going to call those roots or solutions or zeros. Okay, so section 4, we have roots, solutions, and zeros. Basically just the x-intercepts. So how do you find these? You set y equal to 0 and solve. Okay, so let's look at 52. I have f of x equaling 6x minus x cubed minus x to the 5th. So I set it equal to 0. I can factor out an x. So I have x times, if you want to, factor out a negative x. So you end up with negative 6 plus x squared plus x to the fourth. And we can rewrite that as negative x times x to the fourth plus x squared minus 6. Okay. Then we'll want to factor this guy. So it's a quadratic form. So we're thinking x squared plus 3, and then x squared minus 2. From this, you want to take each factor and set them equal to 0. So don't forget this. Some people forget to set that equal to 0. Negative x equals 0. Multiply both sides by negative 1. So one solution is x equals 0. And then from the second factor, x squared plus 3, you don't get any solutions. Okay? You try to solve and it'll be imaginary, so that's no help. The last one, x squared minus 2 is 0. I'm going to solve for x squared is 2, and then do the square root property. X is plus or minus root 2. Okay? So we get these three solutions, or zeros, or whatever you want to call them. Okay. Sometimes you'll go through this process and you'll get multiple root. Like if this was squared, you would have extra copies of this answer. Okay? So that's called multiplicity, and we want to take a look at that because it will change, or rather inform you as to what the graph is doing at that 0. Sometimes it'll go through the axis, and sometimes it'll bounce off the axis. And the multiplicity will tell you which form you're dealing with. So 26, we have f of x equaling 3 times x plus 5 times x plus 2 squared. Okay. So you set it equal to 0. The 3 will never equal 0, right? So 3 does not equal 0, and toss that out. X plus 5, set that equal to 0. So x is negative 5, and then x plus 2 times x plus 2. So this thing right here, if you wrote it out in all of its glory, suggests that we have a multiple root, or root of multiplicity 2 is what they're going to call it. Okay, so for x plus 2, you set it equal to 0, you get x is negative 2, certainly, but there's 2 of them. There's one for this, and then if you set it equal to 0, you get the same thing again. Okay, so what does that mean? Well, we're going to say that has multiplicity 2, and we'll write it with the variable k. So this guy has multiplicity just 1. Okay. So again, it's going to tell you kind of the behavior of the graph. So in particular, if k is even, then it's going to bounce off the graph. Okay? So then you're at that particular 0, you're going to get this bounce effect. So either it's going to bounce up, or if it's already below the x-axis, it'll bounce down. Okay. If k is odd, then it's going to go straight through. So at that particular value k, you'll have something like this. It goes through the axis, or it's going to go in the other direction like this. Okay. With regards to, what's the difference between a higher value and a lower value of k? If k is getting bigger, so greater than just your regular 1, it's going to have a flattening effect. Okay, so in the particular case where it's bouncing off the graph, you'll see kind of more something like this happening, as opposed to this one where it's just ting, very quickly bouncing off. This is more of a skip. Okay, and same goes for going through the axis. It'll get more and more flat. Okay, as the k increases. Okay, this last part, we don't really worry too much about that. It's just more these two guys, the even and oddness, that is really for us. Section 5, though, intermediate value theorem is kind of one of these weird existence theorems. So I think of it like you're trying to find a needle in a haystack, right? And you know, you can imagine maybe you don't even know that the needle is in the haystack. Well, what a nightmare! You know, you're looking for something and you don't even know if it's there. So it helps if you at least know that stupid needle is in this particular haystack when you're looking for it. And a lot of things in math are like that. You're looking for a needle in a haystack, and in math there'll be theorems that say, hey, that needle is definitely in that haystack. You just have to keep looking for it. Okay, so that's what this is. It's one of these. Yes, the needle is in the haystack, and you can look for it and you'll find it. So it's called the intermediate value theorem, and it says if f is a polynomial, and f of a is less than f of b, or vice versa, okay, so greater than or less than f of b, such that we have this kind of picture going on. It's a picture's worth 1,000 words. So here's A, here's B, and we'll say f of A is less than f of B in this particular scenario. And it starts down there and ends up there. What this theorem is saying is that eventually it'll have to go through any value in between f of A and f of B. Okay? In particular, it'll have to go through this point here at C, where f of C is equal to 0. Okay? So it's saying if f is a polynomial and f of A is less than or greater than f of B, such that this scenario is occurring, then there exists a C, there is a C value such that, I'll abbreviate, such that as ST, f of C is equal to 0. Okay? And it basically just says these polynomials are continuous, so eventually it's going to have to hit the x-axis in order to get to the other side. So it's very, very obvious, but and kind of without being able to graph it. So a long time ago, I mean, they didn't have graphing calculators, you know, they wouldn't be able to know this for certain. And I mean, they weren't just working with polynomials, they had harder, you know, functions to work with, I presume. And just knowing that that needle was in that haystack was important. Okay, okay, so 38, let's take a look at that guy. We have f of x equaling x to the 5th minus x cubed minus 1. And we want to find out if there is a 0 between x equals 1 and x equals 2. Okay. So all you got to do is plug these numbers into here. So f of 1 is 1 to the 5th minus 1 cubed minus 1 is minus 1. And then f of 2 is 2 to the 5th, 2 times 2 is 4, 8, 16, 32, minus 8 minus 1. That thing's going to be greater than 0, right? It equals 23, I think. So it equals 23, but obviously that's greater than 0. So here we have this situation, you know, f of 1 is negative 1, and then f of 2 is way up there at 23. Way up here somewhere. So there must be some C value in between f of 1 and f of 2 such that f of that C value equals 0. Okay? So there exists a C in the interval from 1 to 2 such that f of C equals 0. Okay, good stuff. Okay, so let's now talk about turning points. So we're further characterizing the graph with the ultimate goal of plotting these things. And the next section then we're looking at, section 6, is turning points. Okay. So what is a turning point? First, it's the places where the graph goes from going up to going down or vice versa. So in this case, 1, 2, 3, 4, 5 turning points. And you can tell how many turning points, or at least the maximum number of turning points, just by looking at the degree of the polynomial. For example, 38, f of x equals x to the 5th minus x cubed minus 1. This will have at most 4 turning points. It could actually have less, but at most, this thing has, f of x has 4 turning points. Right? So where do I get that number from? It's just take the degree of the polynomial and subtract 1. Okay, so it's take degree and subtract 1, and that gives you 4. So 5 minus 1 is 4. Okay, so finally, let's dive into our graphing strategy. And the way we'll do this is first identify the kind of form or the end behavior. So in the quadratic, what we said was either happy face or sad face. This time we have 4 different kinds of forms. So hopefully you remember those. Secondly, find the X-intercepts and the multiplicity and the implications of that. Thirdly, get your Y-intercepts. We could talk about even or odd symmetry. That makes life a lot easier if you know it's going to be the same on both sides of the x-axis. Okay, that helps. And then note how many turning points. That'll kind of help you check your graph. Okay, so let's actually dive in now and see if we can handle some of these problems. Okay, so this is 42. And in particular then I have f of x equaling x cubed plus x squared minus 4x minus 4. Okay, so first off, its leading coefficient is 1, it's greater than 0, and its degree is odd. Okay. So that tells you the form is one of these types. So it's going up, and then it does something crazy, and then it'll keep going up towards the positive direction. Secondly, then, we want to find the x-intercepts. So x cubed plus x squared minus 4x minus 4. Set that equal to 0. This is a grouping problem, so you're going to factor out an x squared, and you get x plus 1. And then you're going to, over here, factor out a negative 4, and you get x plus 1. And then I'm going to factor out the x plus 1, and I'll be left with x squared, this guy, minus 4 equals 0. So you'll have x plus 1 times x minus 2 times x plus 2. Our intercepts then, negative 1, x equals 2, and then x equal negative 2, and the multiplicity in each case is just 1. Okay, so the multiplicity is odd. That means that each intercept is going through the x-axis. Okay. Thirdly, let's get the y-intercept. So for the y-intercept, you let x equal 0, In these cases, it's easy. This will just be 0 plus 0 minus 0 minus 4. So you'd end up with minus 4. The symmetry then, so you have to check f of negative x and see what happens there. So you end up with negative x cubed plus x squared plus 4x minus 4. Okay. And these are not the same. Okay. It's not even the negative version of the original. Excuse me. So it's basically neither. You can factor out the negative and see if it is, but it's not. So it's neither, even or odd. And then finally, we're looking at the turning point, so max 2 turning points, max 2 TP, I guess we'll call it. Okay, so I'm going to go ahead and graph this thingamajig best I can. So we got -1, there's a guy there, at 2, there's a guy there, at -2, there's a guy there. F of 0 is -4, 1, 2, 3, 4, so you got a guy there. It's coming in from the negative direction. It's going through again, through here, right there. 1, 2 are the max number of turning points, so it seems like it's pretty good graph, pretty good guess of what the thing looks like. Let's think of another, so this will be 56. This time we have f of x equals -2 times x minus 4 squared times x squared minus 25. Okay, so we go through the same spiel. First off, the leading coefficient, and this is one of the leading term you got to sort of get by itself. And this is one of these tricky ones where you're picking this squared times this to give you the leading term. So it would be -2x squared times this other x squared. So the leading term is -2x to the 4th. So a sub n, the leading coefficient, is -2, which is less than 0. And the degree of the polynomial is even. So that's a sad face overall. Should be looking something like this. Okay. Secondly, then you're going after intercepts. It's already factored for us, so you don't have a lot of work to do. -2 times x minus 4 squared is the same as writing x minus 4 times x minus 4. So you have a root of multiplicity 2 this time. And then we got x squared minus 25 is x minus 5 times x plus 5. Okay. So -2 doesn't give you any information, and so you're just looking at x minus 4 equals 0. So x equals 4, but with a multiplicity 2, right? Because there's 1, 2 factors. Then you get the x minus 5 is 0, so x is 5 with multiplicity 1. And then x plus 5 is 0, so x is -5, again with multiplicity 1. Thirdly, then, get your y-intercept. So if you plug 0 in for x, you get -2 times 0 minus 4 squared times 0 minus 25. Okay. So that'd be -2 times 16 times -25. And you're going to get 800. So a bit of a ridiculous value for us, but it's okay. Even and oddness, we could take a quick look at that. It's going to turn out to be neither. Okay. So if you plug -x in for x, you'll get -2 times -x minus 4 squared times -x squared minus 25. That'll be -2 times -x minus 4 squared times x squared minus 25. And the deal is this middle guy is not going to be the same in both cases. So if you put in the same x value, you'll find you get two different y values. So what does that mean in terms of the graph? Basically, you have two different points, one for this graph and one for this graph. So they're not equivalent, right? And then there's no way to kind of factor that out of the problem. If you factor it out, this will become x plus 4, which is still different than this. Okay, so there's no way to even say it's odd, and at the end of the day, you'll just say it's neither. Okay. Then 4, the max number of turning points, the TP is, in this case, the degree is a 4 degree, so the max number of turning points is 3. Okay. So we'll try to put all this information together. We have -5 and -5, and 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. We have some crazy number out here at 800, so I'm just going to do this crazy sort of symbol to indicate that we're way out here at 800 on the y-axis, and that's where I'll put our y-intercept. Okay. The form, it's going up and through -5. -5 is multiplicity 1, so it's going through that point, and then it'll continue up to 800, and then it'll go down at 4. It has multiplicity 2, so it's literally bouncing off at 4. And then at 5, it's multiplicity 1, so it should be going through again and then going straight down. So it has the outer structure of this thing here. Okay, 1, 2, 3 turning points, so it sort of matches up to what we were saying before. And that's about it. Okay.